Hello, everybody. Welcome to today's webinar. Joining me today is Mai Beniguel. She's a wind expert engineer. So, Mai, thank you for joining us today.
Hello, everyone. I'm glad to be joining you today, and thank you for attending this webinar.
So, today we're going to talk about the new functionalities in Meteodyn WT in the new Meteodyn Universe 1.8. So, as you know, I'm the business development engineer for Meteodyn. So, my name is Juan Camilo Daza. So, the first feature we have for you guys today is the fact that you can launch CFDs for multiple directions and stabilities simultaneously. Second thing is going to be you can import stability from a WRF file. We have added the Molas B300 Lidar correction. And the last functionality for you guys today is the Mesoscale-microscale coupling functionality. And then we have some validations for this functionality. And at the end, we have some conclusions. First thing, you can launch CFD calculations for multiple directions and stabilities simultaneously. So before, you could only do this for one stability. Now you can do this for all stabilities. So when you launch computations, you don't have to come back and launch another stability for this. And this is going to save you guys some time. And the direction and stability list is now independent. So let's look at this inside the software. So when you guys are in the software, and then you go into the CFD tab, you click for a new CFD calculation. Here we have the new button, and then you can add just by step or by direction. I'm going to do it by step. So 20 degrees or 15 degrees is usually what we recommend. Then you add them, and later on you can select the stability classes. So usually we recommend you guys to do one neutral, one stable, and one unstable. But of course you can launch as many as you want. So yeah, and then of course you can run a local or HPC depending on your case. I'm not going to do it because, as you know, this takes some time. So let's go back to the presentation. Here it is. Okay, so next functionality is the fact that now you can import stability information from a WRF file. So now you don't have to rely on temperature measurements from your master to do this. You can import this action directly from a WRF file. You can import this for each time step of the time series, or this can be done statistically as well. And you can do it for one or several WRF files. So let's look at this inside the software. So when we go to the meteorology tab, and then I already opened this meteorology. Then on the bottom side here, you have the WRF data, which can be imported. So here are the conditions to import it. I'm not gonna do it today because in front of you guys, because it may take a long time given the size of WRF files. But I already did it for a file previously, so you can see that now we have the stability class information for each time step in the time series. So then you already have this information there, and when you launch CFD calculations, you can either launch CFD calculations for each stability class present in the time series, or just do one neutral, one stable, and one unstable, and the software is going to choose the one that's closest to the one you chose to compute in the CFD calculations for the synthesis calculations. Okay, so let's go back to the presentation. We have added the Molas B300 Lidar correction. So the Molas B300 Lidar is a Lidar from Molas Laser. And as you know, we already had this for the ZX laser, ZX Lidar, and for the WinCube Lidar. So now we have added this for this Lidar. And each time we add this for a specific Lidar, we of course take into account the specific beams of the Lidar, so the correction is done the way it should be, and of course we validate these results afterwards. And all this with the objective to reduce the masked Lidar wind speed ratio. So you can see on the right that before the correction you get a blue line. So the difference between the masked and Lidar can be quite big, it's like 5% or something like this. And then after the correction, we reduce this dramatically, so you can see this in the orange curve. After that, you can of course apply these correction factors to the measured LiDAR data. So let's to see this in the software. So I created a site for this purpose. So it's a very complex site. So as you can see here on the left, we have a site that goes from 300 to 3,000 meters, and the LiDAR is placed. You can see the position here on the right. So right on not quite at the bottom of the hill, but not at the top. So on in a little bit at the middle. So let's look at this inside the software. So when we go to the microscale simulation tab, you can see here the site. I'm going to show you where it is. This is a site in northern Italy. So this is where we are, so in the middle of the Alps. This is why terrain is very complex, and of course you can see the altitudes here. It's a very big difference. So if you want to compute the CFD correction factors, you have to go to the LiDAR data correction module, and then here the first thing to do is to select the site. So in this case, from my case is the outside 2. You select the stability class, then you select the LiDAR element in question. In this case, I only have one, and the correction type. So in this case, it's going to be a Molas LiDAR. Then you can generate your file. This is going to generate a text file. So I'm not going to show you the text file. I already did this and transferred it to Excel. So let me show you the Excel file so you can see the results plotted on a graph. So in this case, we have this correction was actually performed at the location you saw in the software. So on the left, we have the height in meters, and the right, we have wind direction, so every 20 degrees. And you can see the correction factors are very, very high because this site is very complex. So of course, if you guys are planning to place LiDARs in complex or in semi-complex terrain, we really should be applying the correction factors. Okay, so yeah, the different lines are for the different altitudes, as you can see. Okay, so let's go back to the presentation. Next up for you guys is the big functionality, so the Mesoscale-microscale coupling functionality. So the objective here was to combine all the power of the mesoscale models and all the power of the microscale models and take really both effects into account to perform the most accurate simulations. So as you know, the mesoscale model comes from a global model, and then there's a dynamical downscaling to obtain the regional model, and then we're going to use this regional model to input the wind profile into Meteodyn WT so that we can run microscale simulations with a CFD. So Marie is going to talk about this functionality. So Marie, you can carry on.
Yes, I'm going to share my screen so that then later on I can show you the in the application. So Juan presented you an overview of the methodology of the coupling. I'm going to present you the process and the principle, and how the mesoscale data is used in the microscale module, and how it is it can be used in the application. Sorry, I'll go back to where we were. So here you can see on the left classical vertical profile with in the atmospheric boundary layer. What we did is we defined two zones. The first zone is the microscale zone. It's at the surface, in the surface boundary layer. It's the surface. It's the zone that interests us, where the wind turbines are. And we defined a mesoscale zone, which considers the effect above the height of the surface boundary layer. And we have these two zones, and we have two models. So we have the mesoscale model, as described earlier. So it's a regional model, and it provides temporal information and on synoptic effects above the surface, and it considers the impact of regional scales. And we have the microscale model, which is our CFD in WT, so you already know this model, and this introduces the orographical effect at the surface to take all the global topography of the site and all the complexity of the site. So once we have defined these two zones, we will. I'm going to explain the input of the coupling feature. So first we do a classification between classification by stability. So we take from the mesoscale model outputs, we take the temperature, the heat flux, the turbulence, kinetic energy, and we compute the stability, and we classify these stabilities into three categories: unstable, neutral, and stable. And also we classify by wind direction at a characteristic height. We have two types of classification inside the domain. First is a temporal classification. In this case, we classify by stability and direction at each step at the reference point. So we have chosen a reference point that is characteristic of the zone, and this classification is for all the points. And the second one is a spatial classification. So in that case, the classification is done at each point. So that means that one step can be classified differently between several points. This is more used for a bigger area where no reference point can be defined. So now that we have processed the mesoscale data, we have average wind profiles, and we are going to use them first as initial conditions, so as input. So we know how to start the simulation. We also use them as boundary conditions, so at the top of the domain. And more importantly, we use them inside the domain. So we help maintaining the mesoscale profile inside the domain. So at each grid cell of the mesh, of the CFD mesh. So basically, the Meteodyn WT model was a little modified, and the volumetric forces were added in the volume, so that it is added in the mesozone, so that we have this meso profile maintained in the whole domain. And of course, many sensitivity tests were performed to find the best sailing height, the limit between the microscale zone and the mesoscale zone. And in the application, it is a height of 500 meters. In the microscale zone, the wind will evolve freely, and this allows to keep that the CFD do its job and considers all the complexity of the terrain. So the theory behind this might be a little complex, but in fact, in the application, it is very simple in WT. We added a new panel when configuring our site. So along with orography and roughness data to import, you can now import mesoscale-microscale coupling data. There are two types of data. First is a statistical analysis for mesoscale data file. So this is the case where Meteodyn simulates the mesoscale model, did the mesoscale model simulation, and we provide the file. We do the classification between unstable, neutral, and stable for each point. And the second option is you have performed the mesoscale simulation, and you have WRF outputs. So the format is netCDF, and you import them directly in WT. And when clicking on import, there is a process that will analyze the data and classify them by stability and direction. Once the data is imported, in the CFD configuration panel, there is only a new option that is now available, and you just need to check it. So it's very easy, and the CFD computation are launched normally. The results can be displayed and see the mesh as well. The values can be analyzed, the conversions can be monitored. So it's the same as before, basically, except that the coupling has been taken into account. I'm going to show you how it looks in the software. So here I have my site. In my configuration page, I have this new panel. I can import the data provided by Meteodyn. So it's with an extension SAM. It's a home file, yeah, it's very quick to add. I can display the grid mesh, so the grid of the mesoscale cell. And the other option is, I'm going to show you, you have WRF output and CDF output. Here I have taken only few because it might take a long time to process all the data if I take too many files. So for the demo, I only take 4. You can see in the app what is the size of your domain. So here, for example, it's I see the size of the domain that I have, and I can find a thinner around my area, so that I don't need to take everything into account because the resolution will not be modified. It is important to take all the outer domain as it is for the orography and roughness. So when I do import, then it's quick because I have few files, and it's the same. I can display my new. So you see the resolution is still 3 kilometers resolution. So yeah, and now that I have imported my coupling input in the CFD, I can check the CFD. Here I have already launched the CFD, and yeah, you can see that for this I have the available stabilities are neutral, stable, and unstable. So I can launch all types of stability. It is of course important to check if, for example, neutral stability is not available in the mesoscale data. You cannot launch a CFD with neutral stability because there is not enough data to perform the coupling. But you can still launch normal CFD, and then later on during the synthesis, it is possible to combine both CFD with coupling and CFD without the coupling. So let's go back to the presentation here. Of course, we validated our coupling. I'm going to present you several validation cases. The first one was we participated in a benchmark called the ALEC 17. It was for ALEC experiments. It was a site in north of Spain with dominant wind, northern wind. As you see on the left picture, there was a hill on the top, then a valley, and then a very complex area in the south of the site. This is where the interest point was, MP5, and we had several masts with measurements with a 4-day period. And so we were able to compare, and we were very satisfied with the result of this benchmark, with our results and this benchmark, because Meteodyn got the smallest bias between the model and the observation. The second validation I wanted to show you was on the large coastal site in India. So it was a site of 120 kilometers on the western part of India. There was one mast and 3 weather stations, one weather station on the coast, one in the city, and one in the mountain with altitude of more than a kilometer. And so the aim of this study was to compare 3 approaches. The first approach was using only mesoscale data, so WRF output with 9 kilometer resolution. This is displayed in bright blue. Then microscale CFD method, so only WT without the coupling, in orange, and the coupling method in green. We can see the measurement on the graph. Here I displayed only eastern winds, because there was 2 dominant winds, east and west winds, and I displayed unstable and stable conditions. We can see that the coupling gives the best, the closest ratio, speed up ratio between weather station and wind mass, the closest to the measurements, except for in the stable wind Chapati weather station, but otherwise it's the best approach. For more information, if you want to see the western winds and the other stability, the conditions, there we presented this site in a poster in the Wind Europe 2022 event. So the poster is still available on the event website and as well on our website. And the last validation case was a complex coastal site in China, so a site where we had the 1 mast with 3 heads and 24 wind turbines with SCADA data with 1 year of data. And this was a very complex terrain, but it was a coastal area, but there was also region and valley, and there was a prevailing wind in the northeast, so wind from the sea, so with high thermal influence. I'm not going to present the results, as this site will be presented in the next week event, Wind Europe 2023. And we have a poster, the number 186. You can discover the result, and later on after the event, it will be available, of course, on the event site. So I'm going to let Juan conclude.
Thank you, Marie. Yes, concerning the next week's event, we're going to be there. I'm going to be there. So you can come and join us in our stand. And of course, we're going to be publishing the article just mentioned by Marie. So to conclude this webinar, so now you have additional options for wind simulations, and it's going to help you guys optimize the time. We have added an additional Lidar RSD device to improve the compatibility of the software. And regarding the Mesoscale-microscale coupling, this of course improves the accuracy of wind simulations. The method has been validated on different sites, and it is well suited for complex sites with a radius larger than 8 kilometers, which contain strong thermal effects. Of course, for this, you may need assistance from Meteodyn to generate the Mesoscale data. So, of course, we're here to help you to provide that and the coupling. Well, thank you. As I said, thank you very much, you guys, for attending. Have a good evening or morning, depending where you are. And bye-bye.
Yeah, thank you for attending this. Bye.